can also find out another relation for general gravitational force. Now let us say that let's use a general relation for gravitational force. Now if you have any mass, let us say the mass is capital M, and there is a smaller mass M here, then this will be the position vector of small m from capital M. And so this vector means that it has a magnitude of r magnitude, and it is a r vector. It has this particular direction. So let us say that it has a direction of r unit vector. Okay, r unit vector is the direction of a vector joining m, capital M and small m, and it is along this line. Okay, so because you know that gravitational force is always attracted, so this object will be attracted towards the smaller object by a gravitational force, and the same amount of force will be applied by small capital M on small m also. So you'll have a gravitational force applied on both of them. And in general, this gravitational force is given by minus g capital M small m upon r square, r unit vector, and this vector will be given by this. So now what does this negative sign means? This negative sign means that the r unit vector and force vector, they will be opposite to each other. So if the force is in this direction, r unit vector is in the opposite direction, or if force is in this direction, r unit vector will be in this direction. So let us say now if m is larger than small m, so let us try to understand this r unit vector. So let us say this is capital M and this is small m, and it experiences a force of Fg, and the position vector from capital M to small m is r vector, and because r vector is along this radius, it will have a magnitude of r and a direction of r unit vector. So r unit vector is pointing in this direction and Fg is pointing in the opposite direction. Okay, so that is why we use this negative sign here. So now we got the gravitational force, and now let us try to find out the potential energy and the relation between this force and the potential energy. So now we know from equation which we have found out in the last page, which is this one, this equation, where we found that uf is equal to minus integral of f vector dot dr vector plus sub I. So you can write this equation. Okay, and let us put this f here and find out what will be the value of this expression. So it will be integral of, so because we are using gravitational force, so let's use Fg here. So it will be minus g capital M small m upon r square, r unit vector dot dr vector. Now what is dr vector? Dr vector is nothing but it is a small part of r. It is just a small part of r vector. So if r vector is pointing along r unit vector, dr will also point along r unit vector because it is just r. Now if I take a small part from here, it will also point along r. So it will be dr r unit vector plus ui. So r unit vector is nothing but unit vector. So r unit vector dot unit vector will be 1 into cosine of 0. So it will be equal to 1. So from here UF will be equal to integral of G capital M small m upon R square into dr plus initial potential energy. Now we would like to consider that the initial potential energy is 0. Okay, so let us say that Ui is equal to 0. We always assume this because actually it doesn't matter, because whenever we are talking about the potential energy, only the difference matters. So suppose that if you need a potential energy of this point, and then there is an object and it moves to then this point, okay, and so you need the potential energy between these 2 points. So what we will do is we will just think that this is 0 potential energy, and we'll just find out the change. So the whole potential energy of this object will be the total potential energy. So let us say that the initial potential energy is 0, because only the difference matters. So whatever this potential energy will be, that will give you the potential energy difference. So then UF will be equal to integral of G capital M small m dr upon r square. Now how is the r changing? In this situation we are saying that you have this object, and after some time it moves from here to here. Okay, so let us say that let us try to find out the limit of integration for this function. G capital M and small m, they are constants, and we have to find out the integration limit for r. Now let us say you have a mass m and you have another mass small m. Initially it is at a position vector ri vector, and then it moves to another point which has a position vector of rf vector. So it means that this integration, we can take G capital M small m outside and put the limit of integration from Ri to Rf and integrate dr upon r square. So this would turn out to be G capital M small m r minus 2 plus 1 divided by minus 2 plus 1, and integrating from Ri to Rf. So we can also write it as, because this will give numerator will give minus 1, so it will minus G capital M small m, and it will give you r minus 1, so it will be 1 upon r integral from Ri to Rf. So we can also write it as 1 upon Rf minus 1 upon Ri. So let us say that initially that we are starting from infinity. So let us say that Ri was infinite initially. So we brought this mass from an infinite distance and then to another point. So if it is infinity, then UF will be equal to minus G capital M small m 1 upon Rf. So this will be the potential energy for gravitational force. And so because it is a final here and final here, so if we have to generalize this relation, then we can say that it will be, if it is initial, it will be initial. If it be final, it is final. So we can generalize and we can say that in general, this relation should look something like this. For each value of r, there will be a value of potential energy. So now if this is the potential energy, and if we remember, the gravitational force for this potential energy was minus G capital M small m upon r square r unit vector. This was the gravitational force where we started from. to derive this. Now let us try to plot this relation, which is the potential energy versus R. So we have this relation which is minus G capital M small m upon R. Let us try to plot it. Because we are talking about the gravitational potential energy. Okay? So it means this potential energy is actually gravitational potential energy. But it is true for any two masses. Suppose now if the first mass is Earth and this small object is some smaller mass which is being moved from somewhere to Earth. So let us say that this object, it is being moved, this is m, it is being moved from an infinite distance to the surface of Earth, and the surface of Earth will have a radius of RE. So if R is infinite, potential will be 0. Okay. If R is RE, potential energy will be minus G capital M small m upon RE. So it means that when we are moving m from a certain distance, infinite distance, towards the Earth, R will decrease. So from here to here, from infinity to R, in between what is happening is that R is decreasing because the distance between the two objects, small m and capital M, it is decreasing. So R is decreasing. And when R will decrease, potential energy will increase. Okay? And because they are inversely proportional to each other. So we know the behavior at infinity. At infinite distance, if R is infinity, potential energy will be 0. If R is RE, potential energy will be a negative number upon RE. While here also the potential energy will increase, but it will be a negative number. Okay, so it means that throughout potential energy is negative and R is positive. Okay, it will have a positive value. So if we have to plot R versus U, it should be such that R is positive. So in this side R is positive, this side negative. So it will be here. And U must be negative, so U will be positive here, and it will. So it means that this graph, it will lie in this region. Okay, so let's say that infinite distance you have a potential energy of 0. So and then it will decrease, and on the surface of Earth it will have a certain value. So let us say you're moving from infinite distance, and at this point potential energy will be minus G capital M upon the radius of Earth. So this is how this graph will look like. In fact, it should be here because we're talking about U. So it will be minus G capital M small m upon RE. While here the radius will be RE, because along this axis we have radius and along this axis we have potential energy. So we have found out a general relation for potential energy for a general universal gravitational force, which is minus G capital M upon R square into R unit vector. So this is the force. Then the potential energy we found is G capital M upon R. And if we take a derivative of this force, you should get Fg. So this should also be true for this force, because gravitational force is an internal force and a conservative force.